Anybody has any questions or curiosities left about libraries? Hope so. No? Okay, then we leave the bosonic word. Now, I have to confess, I think it's going to be a little bit challenging to describe superstrings, considering that you have not seen most of your supersymmetry before, as far as I can see from the syllabus. So today I will just go to an example which optimistically will tell you both what's behind the definition of superstring theory and perhaps give you a first example of a supersymmetric theory. Now, it's not exactly the first supersymmetric theory you find in textbook, but it's interesting. So, starting point will be essentially parallel to the first lecture. So I would like to ask, suppose I have a theory, a quantum field theory, with fermions. So I look at my Feynman diagrams, there are Dirac propagators. And I would like to rewrite those in the same sort of Schwinger time formalism, and then pass integral over some embeddings of a particle in space-time. So the starting point is the Dirac propagator, which in momentum space for a massless particle is roughly something like that. So I give a massless particle example. If you want to find to know how to do a massive particle, you can just dimensionally reduce. Take one of the components of the momentum as a mass. You can throw away the direction of space-time. So in order to get this sort of propagator from a first quantized formalism, I need to find some way to describe the gamma matrices. Now, as I indicated last time, every time I want to get something more complicated than the scalar, I will have to enrich the quantum mechanics of my single particle in such a way that the Hilbert space of the single particle gets the extra structure that I want. So in this particular case, we need to sort of enrich the quantum mechanics of a particle moving in space-time with some degrees of freedom, which can give me gamma matrices. And such that the Hilbert space of this particle somehow will become a spinor. So to do that, I'm going to introduce fermionic variables in my quantum mechanics. With standard commutation relations. So it should be clear that as soon as I quantize the fermionic variables, I get gamma matrices. So that psi's will play the role of gamma matrices. So how do I rewrite this in terms of this degrees of freedom? I mean, so I will refer to the psi's and to the gammas interchangeably. Okay? Sometimes I write them as gamma, sometimes as psi, depending if I want to imagine them as just operators acting on my Hilbert space, or perhaps as some variables to be quantized. So we know how to write the 1 over p squared. That's easy. So how do we write the p, p mu, gamma mu? Well, let me introduce a second auxiliary variable, Grassmann odd. So when I do the integral over tau, I get 1 over p squared. When I do the integral over zeta, I just pull down this factor. Now, why is this interesting? let's look at these two quantities. So we have p squared, which essentially I want to identify with the Hamiltonian of my quantum mechanical system. And then with this guy, let me call it Q. The main property of this guy is that Q squared equal to H. Which in particular, and also Q commutes with H. So my quantum mechanics sort of has two nice conserved quantities, two symmetries. There's a time translation symmetry. There's some other bizarre Grassmann-Odd symmetry which squares the time translations. Whenever you have something like that, this is called a supersymmetry. So a supersymmetric theory is the theory which has some extra Grassmann-Odd charges, which roughly square to your time translation or in general translation. This means that I can write this quantity as e to the minus tau h minus zeta q. So, roughly speaking, this is something that represents translations in time, and it's some sort of a weird super time, Grassmann-Odd version of time.
Mm-hmm. Is Q a Grassmann-Odd variable?
Yes.
So why have we written Q squared equals to Hamiltonian?
Well, it's an operator. So the same way as bosonic variables commute, but bosonic operators might not commute. Fermionic variables anti-commute, but fermionic operators might have an interesting anti-commutator. So this is essentially the anti-commutator of Q in Q.
I shouldn't be thinking about it as a Grassmann operator.
It's an operator. It's really an operator.
Some operator that has anti-commutation.
Yes. Now here P was a variable, but as soon as we go to Fourier space, so as we did in the first lecture, we Fourier transform, we integrate over the momenta, keeping into account the endpoints. So after you do the Fourier transform, you can try, P becomes an operator acting on x's. We can essentially write this. In this form. So if you take a standard quantum mechanics whose variables are positions and size, and I define my P's by the usual commutation relations. Okay. Then I can write my Dirac propagator in this form. So this became an integral of a proper time and some weird fermionic generalization of it, of a transition amplitude from some initial point at time 0 and super time 0 to some final point at time tau and super time zeta. And And now the plan is to try to write this also as a nice path integral over the. No, the first step is pretty simple. We know the variables. It's something standard. We just write this as a path integral over x and psi with some action. But what's really interesting is to try to do the same thing we had for the standard particle, which is to promote tau to the zero mode of a. Remember in the first lecture. So for the standard, for the particle, for the scalar particle, the final expression we started working with was something like E inverse x dot squared plus E square m plus EM squared the U, right? With the parameterization invariance such that E the U goes to E prime to U prime, and then we fix diffeomorphisms by E equal to tau, by requiring E to be constant. This is what we did. So let's see if we can do the same thing, but in this context of supersymmetric quantum mechanics. So I want to have essentially freedom to parameterize my time and supertime by some local coordinates, and freedom of changing coordinates. So I'm going to introduce some coordinates, U and theta, Grassmann even and Grassmann odd. And I'm going to try to define some supersymmetric version of diffeomorphisms. So one way to think about diffeomorphisms is that they they're transformations that act in this interesting way on derivatives. In this case, it's useful to introduce a notion of super. Well, sorry, let me say this right. Even before we think in terms of this U and theta, right? We just look at this expression, and we call that G of tau and zeta. This is the following properties. First of all, the tau G equal to minus Hg. Now, to understand what happens in the theta and zeta derivatives, it's useful to expand it. So it's 1 minus zeta q e to the minus h tau. Right? So when you deal with the zeta, I get a q by itself. To get something interesting, I need to do deal with the zeta minus zeta plus zeta deal with the tau. So that gives me minus q, e to the minus h tau. Remember, zeta squared is 0 because zeta is a Grassmann variable. So minus zeta h e to the minus h tau, sorry, plus, okay, which is the same as minus q g. Is that right? Actually, I really need the plus here, because if I do qg, there is q zeta q. I need to pass q across zeta to get zeta q squared. So this actually means that a lot of the signs that I write down in the rest of the lectures are suspicious. Because of course I did my calculations with the wrong sign. On the other hand, I would probably get other signs wrong while writing, so they might cancel out. Okay, so this shows you that sort of the natural way to think about time translations is just the usual tau, but super time translations are implemented by this operator. So if I want to generalize this to some sort of diffeomorphism and super diffeomorphism, well, diffeomorphisms are generated by vector fields, so they'll be generated by some operator like that. We call that delta V. And super diffeomorphisms will be generated by something like this. Let's see if this definition makes sense. So it would be nice to check that all sort of commutator and anticommutator of these transformations close to transformations of the same sort. For example, suppose I do delta epsilon prime. Actually, it's still a commutator because epsilon is Grassmann. Now, those equations will consider epsilon to be Grassmann in or Grassmann odd. Debatable. Let's say it's Grassmann odd. Okay. So, what do I get? I get epsilon. So the first thing to observe is that if I take this guy and I square it, I get actually 2 the tau. Sorry, the tau. Because well, almost everything cancels out. And here, I get just 1. So I get the U. So the first thing I get is simply like epsilon prime, true epsilon prime, the U. Second thing I get is when the derivative, the U derivative, actually acts on the generator. So that gives me something like epsilon, theta, epsilon prime, the theta. So let me move theta on the other side. Plus the one we've exchanged. Sorry. Sorry. Okay. So this shows me that actually this definition was not quite good. It was a tentative definition. But see, when I anti-commute to these guys, I get something somewhat more complicated. Now notice that the thing in parentheses is actually half of the derivative of this. So let me amend this definition.
Okay. So I think I'm a little confused. So here, were you computing? I thought you were computing
the algebra vector.
Yes.
But I guess but then you just said the anti. Did you compute the anti-commutator?
The commutator.
This one, okay.
Yes. So I treated epsilon as also a node parameter.
Sure. Okay. But here you're just computing the algebra.
That's right.
Okay.
So after my amendment, this looks like delta of 2 epsilon prime. Now I should show you that this guy does something nice, and this guy itself does something nice. Instead, I'll just show you that this is really the symmetry of something, and so it will be a group. So these two generators represent the transformations which act in a nice way on something called the superderivative, which is defined almost as this, but with opposite sign. So the superderivative has the property that it actually commutes with this operator, anti-commutes with this operator. And it squares to minus standard derivative. So
is that a commutator or anti-commutator on the right?
Suppose.
Sorry. Actually, you joke about it, but there is a convention in which you write things with one curly and one square, and that means do commutator or anti-commutator, depending if the arguments are both odd or not. So if you do a transformation of the theta, because almost everything goes through, all you get is actually, let me see, do it right. Well, there is no hope I get the sign right anyway. But I can write it like that, which is also the same as minus the u epsilon, the theta the theta. So this is a transformation which multiplies the theta by something. Yeah. So if you keep acting with sort of transformations, right? If I keep doing several transformations of this sort, I will always end up with multiples of the theta. Because if I do another transformation, it either acts on this, and leaves the theta there, or it acts on the theta, and it gets until it still has the theta. Which in particular means that the delta V also ends up multiplying the theta by something. And in general, these are the most general transformations with this property. So a way to think about superdifferomorphisms is that they are transformations which, when they commute with this superderivative, they just multiply it by something. So let me write it up somewhere. So it's one-dimensional superdifferomorphisms are transformations with a property. that it gives back the theta. Now, if you at some point you learn some super geometry and super manifolds and things like that, then these are manifolds with even and odd coordinates. You can define vector fields on these manifolds. So on this manifold, there are vector fields, the u and the theta. And somehow this is the theta is sort of a spatial direction inside this tangent space of the manifold. And we only consider coordinate transformations which preserve this direction. Okay. So all of this was just to try to figure out what is a reasonable way to transform my x's and psi's in the quantum mechanics. So I'm going to combine x's and psi's into something that is called a superfield. And I'll just define the action of these vector fields or this superfield just in the standard way. So, for example, delta epsilon of y is just going to act with delta epsilon and get epsilon psi plus epsilon theta du x, which means that delta epsilon x is psi, epsilon psi. Delta epsilon psi is minus epsilon du x. So this is the general structure of supersymmetric transformations. When you study supersymmetric quantum field theories, typically you have some bosons, some fermions, like a scalar field, some fermions. And the variation of the scalar field gives you the fermion. The variation of the fermion gives you the derivative of the scalar field. So you encounter this in higher dimension too. This is sort of the one-dimensional toy model for that. And then you can wonder, how do I write an action which is invariant under these transformations? Okay. So there is a way to do these things using superspace, meaning you really write your action as an integral over both u and theta of something. But for now, let me just do it by hand. So I want my action to start with some x dot squared E inverse. Okay. Now I want to start keep adding pieces to this until I find something that is invariant under super diffeomorphisms. So if I do a super diffeomorphism over on this, what do I get? Oh, first of all, I might make a variation of my auxiliary variable. I don't know what that is going to be yet. So let's leave it unspecified. And then I should probably put a 1/2. Okay. And then I vary x dot. So it gives me equivalent inverse x dot, and then the u of epsilon psi. Which means the u epsilon psi plus epsilon du psi of psi dot. Now, let's look at this last term. In order to cancel it, well, I know how to produce a psi dot, an x dot. So I could just start by adding E inverse psi dot. Actually, let me put again 1/2. So what is the variation of this? I can vary psi, or I can vary psi dot, or I can vary E inverse again. Sorry. I'm going to integrate these by parts. So part of it. Let me just do it. When I integrate it by parts, one of the terms gives me again this x dot psi dot. So I add it to that and I get rid of the 1/2. Then the possibility is to act with the derivative of this. I'm already starting to get the signs wrong, so I surrender most times. Okay. Okay, so we start. This allowed us to cancel this term, because we generate all sorts of other terms. But actually, you can get rid of a lot of the other terms by adding yet another object. So I write it like this. I'm going to add a new variable, which is going to be sort of the super partner of E. Then I run the transformation law for that one to make this work. So this will give me the U epsilon psi times psi, but that will cancel out because psi squared is 0. Then I get epsilon psi dot times psi. I get the variation of chi, whatever it is. And then I get the variation of psi. Okay. So let's see if we can make things cancel out nicely. We're left with a bunch of psi dot x dot psi terms. I'm going to cancel them with the variation of the gravitino. So I'm going to use my delta chi to cancel out this term. To cancel out this term. Yeah, don't believe this sign. And I'm going to use the variation of my E guy to cancel out a bunch of other things. See, here I got back in x dot square and psi dot psi. So this looks like the action. And this is exactly what was multiplying delta the inverse. So okay. So these are the sort of supersymmetry transformations I need to make the whole action invariant under super diffeomorphisms. So now we did the first example of something called supergravity, which is the theory of gravity and supersymmetry. One-dimensional.
Is there a natural way to just simply write down this action without having to add the counter terms? Like,
yes, in this case there is. So first of all, we need to somehow combine these guys into some sort of a superfield as well. So I think roughly the superfield would look like this. Okay. So if I do the variation of this superfield, I get roughly epsilon chi plus theta inverse theta u epsilon plus minus 1/2 theta epsilon u e to the minus 1. So I think this can be written partly as epsilon so the theta plus theta du of the inverse plus a correction which roughly, so this is roughly the same thing that you found in front of the transformation of the theta. So in a sense, so in the same way as, can I say this? When you do diffeomorphisms on E, so E is like the square root of the metric. E squared really is like a metric. So it transforms, it carries indices. So this supersymmetric guy carries some indices in one dimensions. And this gives you the extra transformation term. Carries an index of the same type as the theta. Mm-hmm.
So I suspect ultimately we're going to stick these y's to be the guys I'm going to put in my action. But those x's, when they were bosonic, they were nice and they had like Poincare invariance and all that. What happened to...
They still have Poincare invariance.
Well, isn't that theta going to ruin things?
No, I put the Lorentz index on both. So this is a, you can think of this as a map from some funny one-dimensional supermanifold to standard spacetime. I've not done anything strange and supersymmetric to spacetime. Spacetime is still the usual bosonic spacetime, but the word line has been supersymmetrized. So it's easy to write down the current for Lorentz transformations. There's something like the usual x mu p mu plus psi mu psi mu. Oh, actually, I don't need to. So anyway, all of this was just to say that, yes, this action can also be written as an integral over the u, the theta, of something like the theta y, the u y, the theta square y, probably. I think. I've not checked. I think if you expand this into components and do your data integral, you presumably get the action over there. But I'm not checked. So you should definitely check this. Right, and I'm not sure this is completely true, okay? It's probably true, but I've not. So there is whole theory of supergravity. So it is often the case in supergravity. So you can either do things in components, or you can do things in superspace. And but how to actually do it in superspace, it's often rather subtle. It's more an art than a science to do supergravity in superspace. So I tried to package things together in this E. I'm not actually sure it's the right way to do it. I didn't check it. I did this calculation by hand exactly because I didn't want to get into supergravity in superspace. So it's doable, but it takes a certain shape of mind. I mean, there is people whose profession is to write supergravity theories. It's really, in higher dimension, it can get very complicated to write down an action which is invariant under super diffeomorphisms, and check that all the transformations end up closing. Okay, so what did we do? Well, right. So we ended up with some action, some nice action. Function of x, psi, e, and chi, which has super diffeomorphism invariance. Now, let's check that we can gauge fix it to get something interesting. Now, from this transformation is probably not completely obvious, but the transformation of E squared chi is actually a total derivative. The x squared chi might be, in a sense, E squared chi is the guy that appears in if you invert this E. So you do E, this becomes E plus E squared chi, theta chi, chi theta. So E squared chi is really the super partner of E. If you remember, when I gauge fixed E, we kept the zero mode of E. So in a similar way here, when you do a super diffeomorphism, you can eliminate most of E squared chi, except for its zero mode. So you can use this to make E squared chi into constant. which is nothing but the zeta. Head up there. And after you do that, you can use diffeomorphisms to fix E to also be a constant. Tau. So after you do this gauge fixing, this action becomes something somewhat simple. You should really check me on this too, because I'm not 100% sure. But what you get here, after you rescale tau, so this appears at the end here, is supposed to give you exactly that. So the part integral with this action is supposed to give you exactly the Green's function. So roughly, this sort of first order action, side dot, is the sort of thing you need to get anti-commutation relations like that. So when you quantize this action, you end up with the psi's become gamma matrices, x dot becomes p. This gives you Q, and this gives you the Hamiltonian. So anyway, enough about the spinning particle. All of this, besides giving you some examples of supersymmetry, was supposed to be an invitation to superstrings, in the sense that the way, so there are several different ways to define superstrings, several different formalisms. There is one called the Griswold string, which has a sort of a normal worksheet, which moves in sort of a supersymmetric spacetime. Unfortunately, that's very hard to quantize. Then there is something that's called Neveu-Schwarz-Ramond superstring, different way to realize the same theory, where you do something completely parallel to this. So you start with the supersymmetric worksheet, embedded inside standard spacetime. Which means that you have your, so your super worksheet means it's a worksheet is equipped not just with the metric, but also with the gravitino. It is equipped with coordinates and super coordinates. And then this embedding is described by some superfields. So you end up essentially with a theory of bosons and fermions coupled to some supersymmetric version of a metric.
So what are the indices of chi? Are we saying now we can have more?
There's some spinor in. So the gravitino is something that has spin 3 halves. It has a vector index and a spinor index. Your coordinates have a vector index or a spinor index. Now the fact that the theta is a spinor can actually be seen already in 1D. If you look at how we define the diffeomorphisms. Let me just, is this line visible? Perhaps not. Sì. Okay. See, this is the standard diffeomorphism together with a rotation or a scaling of theta. Theta is rescaled by half of the amount it would rescale a derivative of a vector. So already in 1D, theta was a 1D spinor. So here in 1D, we managed to do things without using 1D gamma matrices. Okay. In 2D, you're going to use 2D spinors. Now, writing down the supergravity theory coupled to these fields is a pain. It can be done. Painful. Perhaps not very instructive. But the point is that this sort of setup still has Wall invariance. Actually, it has Wall invariance together with a supersymmetric generalization of that, which comes from commuting super diffeomorphisms with Wall transformation. So this is super diffeomorphisms and super Wall. Okay. So you can use, when you can gauge fix, you can use this freedom to get rid completely of both the metric and the gravitino. So you can gauge fix in such a way that gravitino is 0, and the metric is the usual diagonal metric. And you end up with something that is a, so you can do it locally, and then you need to glue the patches together. And the patches are glued together by superconformal transformations. Now, I don't want to discuss what 2D super diffeomorphisms are. That's complicated. But 2D superconformal transformations are very easy. They're just the holomorphic version of that. So you have some local variables z and theta, and some antelomorphic variables. And your superconformal transformations are basically, v z, the z plus 1/2 the z v theta, the theta, or the complex conjugate, and epsilon of z the theta plus theta the z. Okay, so they're really the supersymmetrization of the holomorphic coordinate transformation. All that is left from this gauge fixing, well, this gauge fixing has to be done properly, of course. So you have your ghosts, okay, and your.
The thing you wrote to the right of the z theta coordinates, are those the generators of the superconformal
That's right.
transformation?
That's right. So they just look identical to the 1D ones we wrote. except that they use holomorphic coordinates or anti-holomorphic coordinates.
When you say you got superductive morphism and super wild, is that for, what's the form of the action? Is it the same as before, it's just y and y?
It's a supergravity action, which means I don't know it and I don't want to know it.
Okay.
I might have to learn it at some point, but
When we consider the bosonic string, we can either have closed strings or open strings, right?
yes.
But here, when you're adding a Grassmann variable, those boundary conditions won't be like modified somehow?
Not that much. Not that much. So now there is a stress tensor, and there is also a super stress tensor, a supercurrent action, which comes from variations with respect to the Gravitino. So you expressed a boundary condition in terms of constraints on the stress tensor. In the supersymmetric, superconformal setup, you have some constraints on the supercurrent. Again, the constraints are just the normal component equal to 0, pretty much.
Didn't you really use the fact that we're using closed strings to set the delta of epsilon squared chi squared, or chi to be a constant? Because we said it's a total derivative, so we can...
That was in 1D.
Oh, I see, so in general... oh, right, the action. Okay.
No, sorry, you... No, you're right. You're right. I shouldn't say chi equal to... should I say or not say? It's a bit subtle. See, why did I say that you cannot get rid of the zero mode? Because you could if the dots, if your transformation was linear in U, right? So in general, the question if can I really put chi to 0 or not is global. Locally, I can. The same way as I can put a metric in this form only locally. Globally, I cannot. And these superconformal transformations patch together different coordinate systems with this gauge choice, I think. Again, I've not done this in detail myself, but that's what I understand is the story.
Is epsilon here? Is it Grassmann values or is it
Grassmann. I took
epsilon?
it's a bit of convention. If you take a Grassmann value, then these are these transformations are all bosonic.
Okay.
Yes. Yes, it's a Grassmann value. Okay, so as I was saying, this gauge fixing is going to give us some ghosts. And some super ghosts, usually denoted as beta gamma. And these ghosts and super ghosts will essentially combine together with all the matter fields to give us some BRST charge, which will which, among other things, will implement the equations of motions for the metric and Gravitino we got rid of. So, see. Right, so if you remember in the bosonic string, right, we had some negative norm state because we had an x naught. And then the BRST quantization, the restriction to physical states, modulo null states, got rid of those negative norm states. Now because there is a psi naught as well, that also gives negative norm states. And those are killed by these other physical state conditions that come from G. So your physical states are going to be killed by the Fourier modes of T and the Fourier modes of G, roughly speaking. Okay. So now, see, once we get here, everything is good. The action is going to be free, quadratic. These are going to be free fields. They're going to be free fields, free fields, free fields. The square ghosts are still a bit of a pain to describe sometimes because, well, for various reasons. But it's doable. It's all doable with free fields. The physical state conditions are then straightforward imposed. Or if you want to do things properly, you can use your BRT charge. Again, painful, but doable. So there is nothing, no mystery left on the worksheet. Of course, if you want, when you do loop calculations, things can still get complicated conceptually because you need to think about all the possible ways to patch up together a supermanifold out of these sort of flat patches with super conformal transformations. There's a certain theory of super Riemann surfaces that one has to understand to study loop calculations. But at 3 level, not really. So in the next lecture, we'll hopefully be able to just sketch the very basic first steps of the analysis of superstring theory. We will not be able to compute the Weil anomaly of all of this stuff. So I can just tell you now. So this we knew it was minus 26. This turns out to be plus 11. This was plus 1. And the Fermions give plus 1/2. So this theory makes sense as a quantum theory if the dimension is 10. So if mu goes from 0 to 9. And similarly, I won't be able to compute things like the Casimir energy of the ground state. So, but if you allow me to just give those, then we can just do the standard analysis of physical state conditions and at least figure out what is the spectrum of superstrings.